Alright, hi guys. I know some of you wanted some more documentation on the notebooks, and I know we're starting to move into some machine learning things. So I went ahead and I ran through this notebook. So I ran all the cells and I added a few extra comments. But I'm going to go ahead and I'm going to do this video and provide some more in-depth explanations. And hopefully that should help a little bit. I know it's kind of complex, so let me know if you have any additional questions following up, either from reading the notebook or from watching the video or from both. More than happy to help you guys. So in the previous video, I showed you guys how to go from a Colab notebook to a Jupyter notebook to work in the LNL kernel. So this is just kind of how I changed it. So I downloaded this notebook from Colab, and then I just got rid of all the import libraries, or not the import, all the install libraries. So if we look at like number 12, for example, I might have fixed that one too. Like here where you're installing all of them in 11, I got rid of all of that. And then all I did was import the libraries. So here we're importing all of our libraries, NumPy, Pandas, our Atom libraries, DeepChem. And then the next thing you'll have to do is data curation. So here we are going to be creating a few files when we run this notebook. As you see over here, we create a few models as well as a few files. So I set it to be my working directory. So if you don't have a specific folder that you want this in, or if you just want it to go into your home drive for now, your working directory will be /home/ your Purdue username. If you don't know what your Purdue username is, if you hover your mouse over this little file folder to the left, it'll say what your home directory is. So mine says /home/ Wilfong. And then you'll follow the ending of the working directory with this /, and that's just to indicate that it'll be like a file within this file. So I have a tutorials file, and then I have a file for tutorial 10, and then we'll go into the tutorial 10 file. So the next thing we're going to do is we're going to read in our data frame using pandas. So pretty simple function is just the pd.readcsv. You don't have to change any of that. The only thing I did change, if we look at like number 11, for instance, here there's a bunch of displaying the data set, and so you save it as like a URL and everything in Colab, and then you're doing a data frame to CSV, etc. Here you can change some of that, so all you have to do is you have to put where the CSV file is that you saved. So if you just saved it to your regular home directory, it'd just be home / your username / Delaney process.csv. You can keep the SEP and the header that were in the tutorial. And you can also keep the data frame name if you want to. It just makes it a little bit more easier so you don't have to try to keep changing it. So I saved the CSV file that I uploaded into raw data frame as a variable. So the next thing we're going to do is here we're saving our raw df into the data_original, so it's like your original data frame. And that's just kind of creating like a duplicate of it. Because in the next one, you're using your raw data frame and you're printing out the columns. So if you look here, there's a couple of columns. They're printed off better down here. But this is just printing off all the columns. Like I know we've had a few tasks where we've had to print off the columns and report the ones that were important. So here we're looking at the head of it. You technically don't have to put the 5 if you don't want to, because head automatically prints off 5 rows, but this is also really useful. So here's our compound ID. This is different than what we'll usually see. I'm pretty sure these are types like chemical groups or like molecules, but I'm not exactly sure. But that's just like a guess from seeing like thiofen, fenfuran. Those look like they're chemical models, and not just like classes. And then here we have our ESOL, predicted log solubility in moles per liter. That's just a measurement. Here we have our minimum degree, another measurement. Our molecular weight, number of H bond donors, so hydrogen bond donors. that is in our structure, the number of rings. So this could be like benzene rings, like a pentamer, etc. It's been a minute since orgo, but here's our number of rotatable bonds within our structure, the polar surface area, the measured log solubility in moles per liter, and then finally our SMILE string. So if we're looking at this data set, it's obviously a lot more chemical based than our previous ones have been. So don't let that scare you. It doesn't really change that much in the notebook, but it is a lot more chemical based than like the PIC50 value that we currently have. So the next step here is we're using this function and we're creating a new column called RDKit smiles. And what we're doing is we're using our old column, the smiles column over here, because this is our smiles string, and we're using the curate data library from Atom. And what we're doing is we're generating standardized smile strings from the smiles column. So this new smiles column, the new generated smile strings is going to be saved as RDKit smiles. The reason why we're creating these is to have a standardized smile string. The standardized smile string can be used in model calculations later on in the notebook. This is similar to what we did in tutorial 5, because in tutorial 5, we use this exact same function to create our RDKit smiles column, and then we later on use that column to convert the smile string to its molecular weight so that we could then graph it. So basically all this is doing is creating a standardized smile string from the smile string column. The next thing we're doing is we're looking at the head of the data frame again, but we're only looking at the first 4 rows, and we're just double checking to make sure that we correctly created this column. So if you look over here, it's tacked on to the end. Next, we're going to create another column. So based off of the smiles column from our raw data frame, we're adding an inchy key column using the structure utility library from Atom. Inchy keys, it's a IUPAC, International Chemical Identifier. It is used as an identifier for the chemical substances, and all it does is it provides a standard way to encode molecular information. So it's similar to SMILE strings. We're just trying to find a standardized format for it. There's some more information at this website right here, the Wikipedia. But all we're doing is we're creating another column, converting the SMILE strings into an inchy key standardizer, identifier, yeah. So it's just another way to identify the model, and we'll use the inchy key later on in this tutorial. When you do this, you're gonna get a whole bunch of warnings. It's really, really long. Don't worry about that. It all works out, but there's, like when it's converting, it gets some weird warnings, but it doesn't ruin anything, so no worries. Next thing we're going to do is we're going to print the head again, double check and make sure we made this ng key column. Next, in this following cell, we're saving our data frame as data, and then now that we've defined it as data, we're creating a compound ID column that's going to be the exact same as our ng key column. So if you look here in this next cell, we're looking at the head, and we made a new column called compound ID. It's different than this compound ID, but it's also compound ID, and it's just an exact copy of the ng key column. All right, in this cell, we're printing the SMILE strings from the smiles column for the first 10 variables. So this is kind of looking at what they look like. You could print the whole thing if you wanted to. You would just replace this, or you could print the first 20 if you wanted to, or the first 5. You could print from like number 5 to 9 if you wanted to, but we're just looking at the first 10. Here we are using RDKit. This is a library that we imported earlier. It's very important for cheminformatics, but from here we're importing libraries such as Chem, and then ChemDraw, and then iSlice from InterTools. So that's a little different than RDKit, but it'll be used in the same function as the RDKit. So what we're doing is we're creating this variable here called molecules, and we're setting that equal to the chem.mol from smiles column for smiles and iSlice data smiles, comma 9. So what we're doing is we're using the chem library. Specifically, we're using mol from smiles. So this is a function that constructs a model from the smile string. And the smile string is being provided to us from the smiles column in our data frame. And then the ending right here. So here we can say we're constructing it from smiles. So we're pulling it for smiles and iSlice from the data frame or data from the smiles column. And we're only doing the first 9 smile strings. Okay, so if you come down here, it's only got 9 printed off. You could change this to like 10, you could change this to like 11. We're only printing off the first 9. And that's being saved as molecules, okay? So the model that's constructed, or like the model of the chemical model that was constructed is being saved as molecules. And then this next function, we're using another library from ChemDraw, and it's the moles to grid image library, and it returns an image for the structure of the smile string. So we have our structure saved as molecules, and then we're going to create an image from the structure. And so we use draw.moles to grid image for molecules, and it's going to print off these structures for us. So it's kind of complex because we don't have much experience with the RDKit library, but it is very important for cheminformatics. If you follow this, for instance, it'll tell you more about it, so you could just Control F and search through here. But it's a really interesting library, especially for like informatics and visualization. So here, what we're doing is just printing our data frame to take a look at it. So as you can see, we have all the same columns as earlier, as well as the smiles, RDKit smiles, and cheeky and compound ID. As of now, these haven't been important. These first few, up to smile strings, is where smiles is where it kind of gets important. Here, this is our next function that we're doing. So we're setting our column equal to measured log solubility in moles per liter. So here, finally going back into some of the other columns, and we're selecting this one, and that's going to be our column that we'll be using. So what we're doing is we're setting our tolerance here to be 10. This is the percentage of individual response values allowed to be different, so 10%. And list bad duplicates, yes, we want to print the structures with bad duplicates. And then the max standard, this is the maximum allowed standard deviation, but in this tutorial they're setting it to be super, super high. I think that's like 1 million. Is that 1 million? Oh no, that's 100,000. But they're setting it to be super high, essentially to disable the feature, but it's needed for, the reason why they still have that there is because it's needed for the function, because we're using one of the atom libraries for it. Our compound ID is going to be set to our compound ID column. So if we scroll back up here, here's our compound ID column. That's the in-sheet key column that created earlier. And then our smiles column is going to be our RDKit smiles, which is just our standardized smile string column that we made earlier. So here we're creating a new data frame, and using the curate data library from Atom, we're averaging and removing bad duplicates from the column the measured log solubility in moles per liter, the tolerance being 10%, listing bad duplicates, yes. Coming from the data frame, the max standard is 100,000. Our compound ID is our compound ID. And then the smiles column is going to be this smiles column that we defined earlier. And then here it's got this little bitty printout. So the data frame size is 1128 by 17 columns. Here's our list of bad duplicates removed. There's none there. And so our new column was created. What this thing did is it created a new column with the average values called num main. And we will be using this one later on. It also created a couple other columns called perc var, and value num standard. Those aren't as important later on, but essentially what this was doing is it was creating a few new columns with a few new measurements. So here we're going to print the head of our data frame, and as we can see, here's our value num mean, the value num standard, and the percent variation. That's what I'm going to assume that is. And then now, since we have our curated data frame, we're actually going to save this to our working directory. So it's being saved as a curated file to our path, our working directory, and it's going to be saved as Delaney curated CSV. And this function is converting it from a data frame to a CSV file. And if you look over here on the left, I think, yeah, it's this one. Here's my curated CSV file. So you want to make sure that your working directory exists, because if it doesn't, you're going to get a few errors. This next one, it gets a little bit more complex. This is where we're defining our featureizer, the model type we're using, and then the response column that we're using. So the featureizer is going to be ECFP. This stands for Extended Connectivity Fingerprints. This is a class of circular topological fingerprints that are used for molecular characterization. Basically, it's just used to capture molecular features that are relevant to its activity. I'm actually going to show you, I hope it opens and you can see it, but this is an article that I found on it, so it's a beginner's guide for understanding ECFPs. So essentially, when they say circular topological characterizer, it's going to look something like this. So it's just going to be a little bitty circle and a few circles that just characterize the structure that is placed on top of. And then this will be our featureizer for our model. So it goes in depth. It has a lot of good information on this article, but that's just kind of a visualization that kind of puts words into an image for circular topological fingerprints, because that's kind of confusing. But that will be the featureizer that we're using for our model. The model type is specified as RF. This is random forest. A random forest is a type of model that's built in a forest of decision trees, quote unquote. So it's a bunch of different decision trees grouped together. And it's also termed random because it adds randomness to the model while growing the trees. So instead of looking for like the best features in general, it's going to look for the best features among a random subset of features. So it's going to generate a wide diversity that will help create that'll result in it being a better model. But here's an article I have on random forest algorithms. So it's kind of interesting. So here you can see here's like one decision tree. I don't know if it has any actual pictures of it. But if you look up like random forest images, here's kind of what a random forest looks like. So it's got, here's one tree, here's another tree, here's another tree, and it's just a forest of decision trees. And our response column that we're going to be using is this val num mean that we created. So we're just going to be using this one right here and the numbers from it. And this is printing off what our smiles column is. So up here in this previous cell, we defined our smiles column as RD kit smiles. So this is just printing off that it's our RD kit smiles column from our data frame. And then here we're setting our parameters for our model. So we're not storing the data, we're not saving the results. Our ID column is going to be our compound ID, which is our inchy key column copy. The smiles column is going to be our smiles column, which is the RD kit smiles column from our data frame. Our response column is going to be this value num mean column from our data frame. Our featureizer is going to be extended connectivity fingerprints. Our model type is a random forest. Our result directory, or where the models and this like training, testing, and validation data sets are going to go, is our working directory. And then we're going to use this thing called parse wrapper, which is part of the Atom library, and we're going to process our input configuration or these parameters, and then we're going to build a pipeline and train the model, and it's going to be saved as P params. So here, MP equals the mp.modelpipeline.p params. So that's just saving it. Model pipeline is one of the libraries specific to Atom. I believe it's basically how they train, test, and validate their models. And down here, we're actually going to be training it. So we're importing the model pipelines library as NP, or NP up here. And then they're checking the version of it. If you were in Colab, you could hover over np.trainModel to see what the source code was. And here, if we do np.trainModel, we're actually training the model that we saved as NP. So the model that was based off our parameters that we created that were parse wrapped and includes our data set. So this actually takes a very short amount of time. You'll get a few things outputted into your library, and then here they're creating some data visualization. So what they're doing is they're plotting the predicted versus the actual value. So here's what they predicted, and here's the observed value. And as you can see, this one is really linear, but these two are a little bit more dispersed. But that could be something that you could potentially fix in like hyperparameter optimization, which I believe is the 12th tutorial. And here you're printing the p params that you made earlier. So if you go up here, p params is your parse wrapped parameters. And so if you just like read through here, it's going to tell you something. So our dataset key was my CSV file. The dataset was Delaney curated. No data storing ID column was compound ID. Let's see, our response column was value mean. Not saving the results. Smiles column was the RD kit smiles. Let's see. If there's anything else. Learning rate was 0.005. Max epochs was 30. So there's a lot of information here. It can be useful to look into it. So here, Python path. This is our data mine path from Kevin. Search type is a grid. So there's a lot of information there, but it's just printing out the parse wrapped parameters. So now we have our model trained, and it's saved to our directory. And then that's the end of tutorial 10. So this was just about curating and training a model. In tutorial 11, we'll move on and work with a graph convolutional neural network model instead of a random forest one, because we'll be working with both of those this semester. But I know that was kind of complex, and sometimes it's hard for me to explain things like when I'm like, thinking through them. So let me know if you have any questions, or if there's anything that you want me to further explain, either through email, on Slack. You could ask me, you can ask Dr. Allen. I know it's kind of hard, but it's best to have a good working foundation of how we create machine learning models, especially single-task machine learning models, before we move on to the multi-task machine learning models. So please, if you have any questions, anything doesn't make sense, if any of my explanations are kind of scattered, because sometimes that happens, just let me know. Ask me some more questions, ask Dr. Allen some questions, and best of luck with this notebook. And I'll check in with you guys. Thank you. Have a good night.